welcome to Mystere Creations. I'm AJ, your host, and today I'm speaking with Dr. Ethan Seigel. Today's subject is sci-fi, fact, or fiction. Welcome on the show. How are you doing?
Oh, AJ, thanks for having me. I'm doing really well. Happy that it's the start of May. Hoping at last to finally leave the winter weather behind us here in the Pacific Northwest, but somehow I doubt it.
Probably not. We're probably going to have a few cold days ahead, but and quite a bit more rain than we expected this year.
Yeah, well, anything that makes it less likely that we'll have wildfires in the summer is a win in my book. So,
yeah.
You might catch me complaining about how I wish it was spring and I wish it was summer already, but if we can, keep thousands to millions of acres from burning, if we can keep us from having a water shortage, keep the plants and the trees and the vegetation healthy, I'm all for it.
That's true. The more we go into climate change, the more things are going to be kind of up in the air, what's going to go on. But the West seems to be more moist this year, which is great.
Yeah, and look, anything we can do to sort of remind ourselves that there are other things to be concerned with in the universe besides the problems we create for ourselves here on Earth is one of those great things to be able to remember about existence, that for all of it, everything that happens on our planet is just one tiny, tiny corner of this diverse and varied universe we inhabit.
A small grain of sand in a wider universe.
Or maybe even smaller.
Oh, yeah. Well, we're going to get into some questions about sci-fi shows and their accuracy, as well as the physics of some of the propulsion in space, particularly faster-than-light drives and whatnot, as well as other questions of how to find things, how to do things in space.
Yeah, I mean, this is one of the unfortunate things that has both pros and cons about the universe. Space is big and things are really far apart. And that's great for a number of things, including our imagination and including keeping us safe from whatever goings on might be plaguing other stellar systems out there. But it also, at least till this point, has kept us isolated. We have never directly imaged, say, any features on another planet because we can't see them well enough because they're too faint and far away. We don't know of any other inhabited planets beyond Earth, and we want to. We want to know them, we want to visit them, and we want to, if there's anything interesting on one of those planets, we want to meet them and communicate with them, regardless of what they are. I mean, I can't speak for everyone, but I can probably speak to science fiction writers all throughout history that this is certainly one of humanity's biggest dreams.
It's true. I want to meet someone from another planet if at all possible in my lifetime, but somehow I don't think that's kind of in the books for me.
Well, all I'll say is never say never, because sometimes the world can surprise you. And if the world can surprise us, maybe someone else's world can surprise us too.
True. And how would we get there? What ways are open to us now?
Well, we've got to root ourselves in the laws of physics. Like, that's at least a good starting point. So if I said, okay, just, idealize propulsion. Imagine you could accelerate forever and ever and ever without limit. That's actually pretty effective, because if all you did was said, I'm going to accelerate at 1g, at one Earth's gravity towards another target, and I'm going to go and keep accelerating. And when I get to the halfway point, I'm going to stop accelerating. I'm going to turn my ship around, and I'm going to decelerate at 9.8 meters per second squared so that when I arrive at my destination, I'll be at rest, right? No one wants to run into another planet at, a large percentage of the speed of light. That doesn't seem like a good plan. In fact, the alien species that we encounter might take that as an act of war because of the tremendous energies involved. So I would say the simplest way is just go. And believe it or not, if we were going to do that, if we were going to travel in one direction as fast as we could, accelerating at the constant rate of Earth's gravity, at the halfway point, we'd turn around. You could actually reach any planet or star you chose in a single human lifetime. If we picked a 20-year-old to go on that journey, anywhere in the observable universe that we could reach, they would be able to reach before they turn 70 at that plan, which is kind of an amazing property of relativity and time dilation. But the problem is, they wouldn't age on the ship because they're moving so close to the speed of light. But everyone back home would age. So if they wanted to go somewhere else in the galaxy that was 30,000 light years away, they might only age 30 or 40 years, but we back home, we'd, who knows if humanity would still be around 30,000 years from now. You start talking millions or billions of light years, and, we don't really appreciate that so much. This was one of the problems with the original Ender's Game and Speaker for the Dead series that Orson Scott Card wrote, where they said, this is originally how we're going to do it, and we need some better device for that. So Star Trek made a better device. They said we're going to have warp drive where we can exceed the speed of light. And other places have said we're going to have a hyperdrive like Star Wars where we break the speed of light. Some places say that they're going to do something like fold space or leverage wormholes like Deep Space Nine chose. So these are all ways to circumvent the special relativity problem that, you don't want everyone to have to get older waiting for you to take your journey to the stars. So these ways are tricks to get around Einstein's special and general theories of relativity, to say that you can reach somewhere or communicate with someone or even travel interstellar distances without having to wait for thousands or millions or billions of years to pass for the people you leave back home.
What's the most efficient drive that you can see in those that you suggested we could possibly use, like hyperdrive, warp drive, folding space?
Well, when you talk about efficient, right, normally we mean something like energy efficient, like which will get you there for the smallest expenditure of energy that you can fathom. And if that's what you mean by efficiency, unfortunately, it's none of those. It's the old, let's just use propulsion. Get some fuel. Maybe you want a mix of matter and antimatter as your fuel. That's the most energy efficient you can get, because for every gram of antimatter you bring on board, all you need is a gram of matter, which, hey, look, is very abundant here on board a spacecraft that we built. And then whatever you annihilate just becomes energy via E equals mc squared, and that's 100% efficiency. If you only count the antimatter, it's 200% efficiency. And all of that energy can go, because the matter's free, right? You have matter everywhere, so antimatter then is 200% efficient. So that's great. That'll propel you really, really far, really fast. But you have that time dilation problem, right? If you go to somewhere 40 light years away and you're like, I want to know what's on that planet's that orbit TRAPPIST-1. And so, you go there, and maybe getting there, the journey only takes you 6 months, and maybe coming back, the journey only takes you 6 months. Even at 40 light years distance back on Earth, where you've aged 1 year on your journey, everyone back home has aged 81 years on their journey. So that's no good, right?
No.
You age 6 months and 40 years for back home people, and then you come back. It's 6 months for you, but it's 40 years and 6 months back home for everyone. Not a great plan. So in terms of time efficiency, the best bet would be something like a wormhole, because that can literally just take two different places in space that appear to be disconnected. But just like if you have a sheet of paper that you fold and connect two disconnected parts, and you imagine poking through from one spot to the other, if you can do that with something like space, then you can travel from one location to another that could be separated by hundreds, thousands, millions, or billions of light years instantaneously. So in terms of time efficiency, in terms of aging efficiency, a thing like a wormhole or folded space that allowed you to just pop out of one location and into a disconnected other one, that would be the most efficient one.
Okay. In doing that, what is the physics of actually folding space?
So this actually depends, interestingly enough, on the topology of space, right? We normally, when we think of space, most of us think of like this three-dimensional grid-like thing that you can imagine a grid is down and it goes on forever in all three dimensions. But what if it isn't like that? What if instead one location is sort of mapped onto another location? It's sort of like imagining, what if I took, Los Angeles in the United States and Shanghai in China, and instead of drilling a tunnel through the earth that connected Los Angeles to Shanghai, what if instead I could suck both of those points down into the center of the earth and have them both meet there? And then you could just travel from Los Angeles to Shanghai pretty much instantaneously, even though they're set apart. So that's kind of how you'd have to fold space, is you'd have to think in one extra dimension. Normally you think about the earth as being a sphere, yes, but it's really just the two-dimensional surface of the sphere where people live. People don't live in the atmosphere above the earth. They don't live subterranean, under the ground, beneath the earth. They don't live in that third dimension, in that depth dimension. So if we did, right, like in the universe, we say, okay, we have these three spatial dimensions, but what if there's an extra one that you can imagine, like you would just pluck someone out of one location and plunk them down in another? That'd be the most efficient way to get there, but you'd have to have a tremendous amount of energy to curve the fabric of space enough that it can do that. Some have hypothesized, let's connect a black hole to a white hole. White holes don't exist as far as we know, but they could. And that connection would allow an object to pass through. That idea is something like a wormhole that people have talked about. You can say, okay, well, what if we just fold space so that an object appears like it's moving along and then whip, it disappears and reappears somewhere else in the universe? That's more like a folded space thing. Something that's a little more curious is Star Trek, which is kind of like a hybrid between those, because their idea of a warp drive was actually proven to not be inconsistent with physics in the mid-90s, when a physicist named Miguel Alcubierre showed that what you can do is, if in addition to having positive mass with positive energy, if you also had some form of material in the universe that had negative mass or negative energy to it, you could have a space-time that basically worked where it had like a stable bubble, and in front of the bubble, space was compressed. So it was smaller distances were in the direction you were moving, whereas the way you compensate for it is behind you, space gets the opposite of compressed, what we call rarefied. So compressed in front, rarefied in back, and that way, if you travel ahead through the compressed space, you can actually beat the speed of light if that light has to travel through uncompressed space. So that's the Star Trek way to do it, physically possible if there's negative mass or negative energy. The wormholes may or may not be possible. You'd need some sort of white hole to exist, which we don't have in the universe as far as we know. And folded space, we could do that. We would need at least one extra dimension of space over the three we know of, but it could be out there, and if it can, then space could be folded, and we could simply pop out of one location when we pop into another, and that could work. But all of them rely on something speculative unless you don't care about everyone you leave back home aging at their normal rate.
With the Star Trek warp drive and the negative energy or negative mass in this, is that possible for us now, or is this something that we will have to look at in the future? Well,
it's not possible right now because of two things. One is we don't know of anything with negative mass or negative energy. But two is that you can make something that effectively has negative mass, and this is more of a technical thing. So you can say, okay, look, on average, the universe is not completely empty. On average, there's some amount of matter and energy present in the universe. So if you want something to behave like it effectively has a negative mass, all you need to do is create a region with below average energy density. If you said, let's say there's 1 proton per cubic meter of space on average. Well, if I can create a region of space with 0 protons per cubic meter of space that's really big in one direction, then I can say, now this has below average density, so it's acting like it has negative energy relative to what that mean level is. This is a hugely technical challenge, but it's not a physically impossible one. The other thing, though, that could immediately catapult this from fiction into reality is this. We know that mass, like anything that has energy, has mass, right? E equals mc squared. What we don't know is how gravitation treats all forms of that. We have not been able to detect how antimatter behaves in a gravitational field. We have recently, for the first time, created neutral antimatter, where we've made anti-atoms. And one of the great experiments that's going on right now at the antimatter factory at CERN, where the Large Hadron Collider is they are doing experiments where they are creating a bunch of anti-atoms together, confining them, and then turning the magnetic fields that hold them together off. Most of them will scatter away, but some of them should just start to fall in Earth's gravitational field. Almost everyone who's doing this experiment expects that antimatter will fall down at 9.8 meters per second squared, just like matter does. And if it does, boo. Victory for physics, it does what we think it should. But if it doesn't, if antimatter falls up, then we will have discovered, to our surprise, that antimatter anti-gravitates, and all of a sudden, all of our negative mass warp bubble dreams are a physical reality. So there's a reason we do the experiment, right? Because we don't know until we do it. And no matter how unlikely we think it may be, we want to know if it's possible.
What's the possible explosive outcome of that, though?
The possible explosive outcome? Yeah. I mean, hopefully very little. These are tiny, tiny amounts of antimatter, and we would need to make a lot of it to make warp drive possible. Right now, we're talking about individual anti-atoms, and realistically, we would need something like planetary masses worth of anti-atoms to make a working warp drive. But, go big or go home, right?
It's true.
So, so dream about it and then you work about making it more efficient. So see if it's possible. That's the first step. You gotta crawl before you can run, and we want to run, and we're trying to learn how to just sit upright at this point.
That's true. Once we get into space, we start exploring, how difficult would it be to find water, minerals, and other resources?
You know, that's actually something we're getting pretty good at now. We're still in our infancy here on Earth. You know, just over 30 years ago, we didn't know of any planets around stars beyond the sun. Today, we know of more than 5,000. We have been able to characterize many of them through two processes. One is called transit spectroscopy, which means when a planet passes in between its parent star and our own eyes, we can see the starlight from its parent star filtering through its atmosphere, and that tells us what's its atmosphere made out of. If we can perform transit spectroscopy, we can know, oh, look at that planet over there. What's its atmosphere made out of? Is it nitrogen and oxygen? Does it have carbon dioxide? Does it have methane? Does it have an ozone layer? Have the 1980s come? Did they invent white rain hairspray? Are there chlorofluorocarbons in their atmosphere? Do they have an ozone layer? Do we see biological signatures of life? Do we see, you know, what are all the things we see there? That's an easy way to see what's there in space. But another way you can do it, what we're hoping to do with near future telescope technology, is to take Earth-sized planets and say, even though the parent star you're orbiting is so bright relative to you, we can block out that star's light and view just the light from the planet. And if you can view just the planet's light, if you can directly image it, that can tell you all sorts of information, including, are there oceans, are there continents, are there cloud covers on it? Is there liquid water? Is there gaseous water? Do the continents change color, like green and brown with the various seasons? So all of these things, these are going to be achieved, for my money, before the warp drive is achieved. So right now, we're getting actually very close to finding water, minerals, other resources. This is one of those things that I think in the next 10 to 20 years, we're going to see real progress on, that I would be very surprised if by 2040, we didn't have a planet that we had identified and said, oh, if we're going to go anywhere interstellar, this is where humanity needs to go first. This is the big red apple on the lowest hanging branch of the tree of life in the universe beyond Earth.
How many planets are there that are calculating to be Earth-like?
Of the ones that we define as Earth-like, which is, say, Earth mass at about the same distance to have the same temperature. So if it has a thin atmosphere, it could have liquid water, oceans, and the ingredients for life with enough heavy elements and enough of the precursor elements that life is possible. There are anywhere from about 5 to 20 billion Earth-like planets, by that definition of Earth-like, in the Milky Way alone. So we don't know how many of those actually have life on them, how many of them became inhabited planets, how many of them gave rise to a complex, differentiated, intelligent animal, much less became technologically advanced and are still there without having nuked themselves out of existence. But this is part of why we know there are billions of chances out there in the Milky Way alone. And the Milky Way is just one of multiple trillion galaxies in the observable universe. So there are a lot of chances, and it's really up to us to learn, to teach ourselves by scientific investigation how many of those chances have actually led to legitimate discovery. How many of those chances turned out to be winning lottery tickets. The big puzzle we have is we know here on Earth we've won the cosmic lottery, but we don't know what the odds of winning this prize are, and we don't know what the other prizes out there could have been. We assume, but we're not even sure, that we won the grand prize in the universe by getting to exist. But it's possible that somewhere else out there, some species on some planet is leaps and bounds more successful than even our wildest imaginations will allow us to run with.
How close are we to generating artificial gravity in a space station or spacecraft?
Well, there are three ways to do it. One, the easiest way is if we discover this negative mass material, because all you do is you put the massive material on the bottom and that attracts you down, and the negative mass material on top and that repels you away from it. If you hold that, just like if you had a parallel plate capacitor with electric fields, you will generate artificial gravity that always pulls you down. We don't have that negative mass stuff yet, so if you don't, the other two ways to do it are, one, like 2001: A Space Odyssey does, and you have a large enough spherical or circular station that spins, and then the outer rim is down and the inner rim is up. You really need things to be big enough if you don't want to get dizzy from that. We really need something that's relatively big that rotates slowly. Otherwise, those centrifugal forces, that will really mess humans' physiology up. So realistically, if we wanted to do that, we'd be talking about a big thing, something that was maybe a mile from end to end. But that's not so bad in science fiction terms. The other way to do it is to just do that very first thing I talked about, keep accelerating. Einstein had what he called his happiest thought. I mean, you don't think of Einstein as being a happy guy at his own thoughts, but he was. His happiest thought was called the equivalence principle, where he was thinking about what's the difference if I'm in a closed room where I can't see out, if this room were located at rest on the surface of Earth versus if this room were in a spaceship that was accelerating at a constant rate of 9.8 meters per second squared. And these are equivalent to a person in the room. So I would say if you want to make artificial gravity, just keep constant acceleration at whatever gravity you want, and there you go. That's the way to do it. Now that requires constant fuel and constant energy and constant expenditure, so you better bring enough. But if you do, that's the easiest way to make artificial gravity.
What are the effects of bombs, particularly nuclear bombs, in space?
So a nuclear bomb would actually be pretty effective in space because, unlike conventional bombs, it doesn't require oxygen to trigger a combustion reaction. There is no oxygen in space, so most of your conventional bombs are not going to work. But a nuclear bomb can. A nuclear bomb can work. The big thing that we're not used to seeing is instead of making a mushroom cloud, which is the shape you make when you have an atmosphere with a gradient on a planet with gravity, you would instead make a spherical explosion. The explosion would be spherical, and it would make a pure shockwave if you set off a nuclear bomb in space.
What would the effects dissipate quickly, or would it take longer to dissipate?
You know, dissipation is very straightforward. It goes as 1 over the radius squared, right? Just like anything that emits light, radiation particles, it spreads out in a spherical shape. So if you are twice as far away as someone who's closer to the blast, you only get 1/4 of the effects: radiation, blast wave energy, concussive force, momentum of the particles. You only get 1/4 of that. You go 10 times as far away, you only get 1% of it. Interestingly enough, one of the best strategies for deflecting, if we had a rubble pile asteroid or comet that was headed for a collision course with Earth, you would not want to nuke it right on the surface. You'd want to nuke it a small distance away from it so that the blast wave didn't fragment the object into a bunch of tiny little things, but rather would heat it up and basically bake it to give it like a sort of artificial crust that would keep it from breaking apart. So the effects of bombs in space depend on what you're bombing, right? There's a smart way and a not smart way to do it, because what you don't want to do is make more problems by yourself, and now your problems are radioactive because you nuked it.
Yeah. And could nuclear energy be used in spacecraft as a kind of an almost endless source of energy?
That is one of the ideas, right? When people talk about propulsion, we are still using chemical-based fuels for our rocketry propulsion, which is horrifically inefficient, right? If E equals mc squared, how much of that mass are we turning into energy? Nuclear reactions are hundreds of thousands to millions of times more efficient for the same mass of fuel versus chemical rockets. So if we could have a fission-based or a fusion-based nuclear engine, that's really the best in terms of energy efficiency we'll be able to do until we perfect matter-antimatter transport and annihilation.
It'd be interesting to see an actual spacecraft with a nuclear engine. How close are we to doing that? Can we actually do that now?
We can't do that right now. This was, ironically enough, something that was proposed in the early 1990s when George Herbert Walker Bush was president. He had proposed a 30-year plan to get humans to Mars. That would rely exactly on this nuclear propulsion technology. And unfortunately, as often is the case, when something takes more than one presidential administration to see from beginning to end, other political interests have come along and derailed it. So that was one that there was a plan for it, and as soon as the first defunding of it happened, it never really saw the light of day again. But we could, and there are many, many reasons that I and many others think that not only the U.S. government, but world governments everywhere should be investing orders of magnitude times more in the development and perfection of nuclear technologies for power use, for power generation, and as the solution to the energy crisis in a clean and green way than we currently are. But there are many political reasons why that is not happening, not so many scientific reasons why that isn't happening.
The pushback of nuclear is the nuclear bomb. The people think of nuclear energy as a nuclear bomb, and the two are they're much different. Can you explain the difference between a nuclear bomb and a nuclear reactor?
Yeah, I mean, for me, they're very different. Now, it is true that some nuclear reactors and the way that they operate it will produce as a waste product material that can be used as fuel for a nuclear bomb. That is where they're connected. But that's also, to me, like saying, oh, well, we shouldn't run coal power plants or oil power plants because chemical reactions also make weapons. They also make explosives and chemical weapons. And yeah, they do. But saying, oh, something is a chemical and therefore we shouldn't use it is like, no. There's this whole science of chemistry. Well, there's this whole science of nuclear physics too. And it has peaceful uses and it has wartime uses. And you can be in favor of the peaceful uses of it for the benefit of all humankind without being in favor of the weaponized uses of it. So I think, to me, this is just really a question of, if all you do is you hear nuclear and you think bombs and power and that's the same, that's like hearing hydrogen and oxygen and thinking that water and hydrogen peroxide are the same thing, and you had better be real careful about every clear liquid you ever encounter because, oh God, that hydrogen peroxide is lethal. No, like there's a difference. Like you don't just get to say it's a chemical, it's going to kill you. You don't just get to say it's nuclear, it's all bad. Bring a little nuance into your life. You'll thank me for it.
Fighting in space in a ship, how do we overcome gravity, and how would the ship overcome G-force and be able to stop on a dime or change direction?
Well, this is kind of a challenge, right? Because when you think about fighting in space, you probably think about like Star Wars and the dogfight styles that they have. And the thing that always bothered me about watching the old Star Wars movies is they would have like their engines get hit or something, and the ship would, and it would slow down and stop. And that is not how things work in space. Space, you obey Newton's first law way more often than you think. And for those of you who don't remember, Newton's first law of motion is an object at rest remains in rest, and an object in motion remains in constant motion unless acted upon by an outside force. So that's the real danger in space, is that wherever you go, you're just kind of free falling it unless you're accelerating. So dogfighting in space, having a space fight, is all about maneuverability and being able to change your direction and your momentum and your speed quickly. That's the difficulty. So if you want to change your position, you need the ability to accelerate quickly. That is a problem for G-forces, because fast acceleration means a lot of strain on the pilot. That's why fighter pilots go through G-force training exercises. That's why they wear special compression suits. That's why, like, all sorts of precautions are taken against human beings losing consciousness when accelerating quickly. But that's the key in space. It's not about altitude. It's not about speed. It's about maneuverability. Maneuverability is the key to winning a space battle. So just as we did see in Star Wars, a small maneuverable fighter can beat a big lumbering titan of a ship any day. And that is likely to still be true.
Everyone likes the idea of dogfights in space. How practical would that actually be?
You know, all I think of is how difficult and unforgiving the environment of space is, and how difficult it is, and how resource intensive it is to put a presence out there into the universe. So the idea that we would be petty squabbling and blowing each other's ships up for whatever reason, I guess that's the sort of idea that only a human could come up with. So, I'm not really a fan of it, but if it has to happen, I do want the good guys to win. So I'll just say that.
All right. How much force, in layman terms, would it take to escape the gravity well of a black hole?
Ooh. So when it comes to a black hole, if you are outside of the event horizon, the closer and closer you get to the event horizon, the bigger and bigger a force you'll need. If you're right at the edge of a black hole's event horizon, it would take, pretty much an infinite amount of force to get you out in the nick of time. Because as soon as you cross that event horizon, I got bad news for you. Every way you would go takes you down to the central singularity. And that is what you want to avoid. So the only way to break out of a black hole's gravity is to have the foresight to start doing it before you cross the event horizon. Once that event horizon is crossed, it's game over. The closest we've seen to a TV show or a movie portraying it accurately was probably in the movie Interstellar. That depiction of what it would be like to fall close to a black hole is probably close, but that leverages the idea of a wormhole, that when you do fall in, you can reemerge somewhere else. That's speculative right now, but if you want to go into a black hole and not get destroyed forever and ever and ever, that's what you have to hope. You have to hope, okay, this looks like a black hole to me, but I really hope it's a wormhole that's stable and is going to take me somewhere else safe when I get to the other side of it.
That would be my hope.
Yeah, but it's that sort of thing where you don't get to find out until you go inside. So, cross your heart and hold your breath and hope that you've got some life left.
Oh, that's where a probe is probably the best way to do it.
That's a difficulty too, though, because once you cross the event horizon of the black hole, you'll never learn anything about that probe beyond that point. So that's the sort of thing where it really is wishful thinking, because the only way to know for sure is to follow that probe in there and see where it winds up.
Okay.
Or, I guess, wherever the probe does wind up, you can say, okay, now probe, send your signals, but you have no idea where it landed, right? So wherever it reappeared, if it reappeared somewhere, it can only send you signals at the speed of light. So if it's 40,000 light years away or 40 billion light years away, you'll have to wait a really long time for those light signals to reach you. The bigness of space is unforgiving.
Yeah. Well, in space, going towards a planet, how would you avoid that planet without maneuvering?
Oh, okay. So what you really need to do is, right now, you can look out at all of the different objects in space, and if you look sensitively enough, you can catalog what are their three-dimensional positions. Where are they, in all three dimensions? But what you really need to know is, once you figure out how far away they are, then you also need to figure out how fast are they moving and what direction in three dimensions are they moving in. Because when you plot your trajectory to your destination, you want to make sure that none of the things that are out there are going to get in your way as you travel to them. Right? Because you're not seeing objects where they are right now. You're seeing objects where they were when the light that they emitted back then is arriving at your eyes right now. So you are seeing things as they are in the past, and they're farther in the past the farther away you look. But when you go and you travel towards them, the objects that you're seeing as they were when they were at a time that was longer ago, not only will more time have elapsed from then until now, more time is going to elapse from now until your ship is at the same location where that object's going to be. So you need to know, where are these objects, how are they moving, and how will that evolution work as we go into the future. That's the only way to responsibly plan out where will I go so that I don't hit a pulsar, neutron star, white dwarf, black hole, planet, etc., much less a bright and luminous star.
Habitation of other worlds. How close are we to be able to do that?
Are you saying to inhabit another world, or are you
Yes.
saying to find another planet that's already inhabited?
No, to inhabit another world.
Unfortunately, we haven't found any other planets that are already coming to us suited for human life on them. So I would say the closest on the horizon thing would be to bring a self-enclosed environment with us, where we know humans can survive, and to build that on a presently inhospitable planet like the moon or Mars or something that's right here in our own cosmic backyard. As far as having a self-sustaining habitat, that's going to either require something that takes a much longer time to do, like terraforming, or it's going to take the discovery of a planet that comes to us with the right conditions for humans to inhabit it as is. But since we don't know of any inhabited planets beyond Earth, much less an inhabited planet that's been transformed by its biology in a way that would be compatible with humans living there today, I bet on the thing we can do first. Bring our own environment with us. Make an environment that's hospitable to humans. Don't let Mark Watney go. He's bad luck. But other than that, that's probably the best plan you have.
Which planet in our solar system or stellar body in our solar system would be best for us to transplant enclosed environment to?
This is not the answer you want to hear because it doesn't require dreaming as big, but the moon, because it's the closest. The moon's the closest. It's made out of the same stuff the Earth's made out of. Bring water, bring an airtight container, bring an atmosphere, and you're good to go. That's how you start it up. So pick the lowest hanging fruit first. Take the easiest obstacle, learn how to overcome that, and then take those lessons you learned elsewhere. We tried to do an analogy of that on Earth when we did the Biosphere 2 experiment in the 1990s here on Earth. And although the experiment failed, we learned a lot of lessons about what to do and what not to do. And so I like to think that look, we want to think of things as a revolutionary process, but realistically, science is an incremental process. And so don't be afraid of taking small steps as goals towards a larger, longer-term step. When we try to take all the steps all at once, that's when we wind up failing.
This is off of our topic, actually. Can you explain the idea of a tesseract? And is there any real-world study or application of it?
So a tesseract is basically this idea that there are more spatial dimensions out there than just the three we have. So you can say, okay, if I had a one-dimensional object that's a line, if I had a two-dimensional object, like what if I moved that line through a second dimension, I'd get a square. What if I took that square and I moved that through the third dimension, right? Then I'd get a cube. A tesseract is what you get if you move a cube through the hypothetical fourth dimension. If you move that, the shape that you get out, like this cube that goes up to 4 dimensions, this hypercube, that's what a tesseract is. So, if there are higher dimensions out there, that is one of the theories you can implement to make all sorts of wild things possible, like folded space that warps you instantly from one location in 3-dimensional space to another location in 3-dimensional space. So if we have more spatial dimensions to the universe than the 3 we know, that's why we'd be interested in something like a tesseract. And that's how something like traveling through folded space, so you'd pop out of one location and into another instantly in 3 dimensions, that's how that sort of thing would be possible. It's a little different than it was described in A Wrinkle in Time. Apologies, Madeleine L'Engle. But that's the mathematics and physics of a tesseract and higher dimensional folded space.
In higher dimensions, is there any evidence of that?
Not yet. There are people looking, there are many people hoping, and there are people writing many types of incarnations of theories about it. But experimentally, observationally, we don't have any good evidence for it that, stands out as signal above the noise.
Okay.
That's not an excuse not to look. It's just a reality check that if this is a secret of nature that's out there, it's a secret that nature hasn't given up yet.
And, of course, we keep searching for more evidence daily.
Oh yeah, I mean this is a never-ending thing, right? Every day that goes by, we're taking more data, we're listening to more things, we're seeing more things, and it's the full suite of everything out there that informs us as to what we know. When we talk about the number of Earth-like planets that are out there and the number of chances for life that are out there, you have to remember that we have seen only a tiny, tiny, tiny fraction of what's out there. And just because something isn't the easiest imaginable thing to discover doesn't mean that the search isn't worth it, doesn't mean it isn't worth looking for. So let's continue to look to the best of our abilities at each and every moment in time.
So discount nothing and continue searching for everything.
Yeah, and do it in an informed way, right? Don't search only for the low probability, high reward things, but also don't search for the most mundane thing that you think might be the most ubiquitous. Search for it all. And, as soon as, because the worst thing to me is to replace the surety, the certainty of I know because I looked and I learned with I think and therefore it isn't worth looking.
Good words to end the show on. Have you got any new projects that you're working on right now?
The two big ones that I'm excited to share because, I am known for Starts with a Bang, my blog, podcast, etc. The two big projects I'm working on is right now I'm in the process of writing a book with a collaboration of wonderful space artists and designers called the Encyclopedia Cosmologica, where we are putting together an illustrated and beautifully told story of the history of the universe, of all of creation, from the Big Bang to the present day, and we're doing it in 100 million year chunks so that every time you turn the page, you're stepping forward 100 million years in cosmic history. And the second project I'm working on is I am co-writing a children's book about science called The Littlest Girl Goes Inside an Atom. And I am delighted about this prospect because I think there are all sorts of wonderful books out there for children of all ages, but not very many of them treat the child as though the child is intelligent enough to understand what's really going on in reality at the most fundamental levels, at the largest scales, on the smallest scales. And I am a big fan of just putting that out there because if you speak to them on their level, kids can understand oftentimes even more things than adults because they aren't held back by all of the experiences that a human adult has had in their life. So these two projects, the Encyclopedia Cosmologica and The Littlest Girl Goes Inside an Atom, I hope that certainly by the end of 2023, next year, that these projects will be completed and out there and ready for you to buy. But I'm hopeful that they'll come out even sooner than that.
Great. Well, thank you very much for coming on with us. And hopefully we can talk to you again about some other things.
Thank you very much, AJ. I'm sure we will.
All right. Take care.
All right. Bye-bye.
We wish to thank Ethan for joining us again. With Ethan's wealth of knowledge and understanding of physics and cosmology, this was a very intense collection of thoughts. Please check out his books, Encyclopedia Cosmologica and The Littlest Girl Goes Inside an Atom. I'll post where to find these in our show notes. Please like, follow, and subscribe on whatever platforms you follow us on. Have a great day, and we'll see you soon.